Thank you. This is a joint work with Tamir Khazan and Tomer Cohen, who gave the previous talk. Let me start from an example, and this is the well-known bandit shortest path problem, where it is a game between a learner and an environment. There's a directed acyclic graph G with two vertices S and T. And at every round T of the game, the learner has to choose an ST path. Simultaneously, the environment assigns a loss to each of the edges of the graph. So these losses can be adversarial, not necessarily stochastic. And then the learner suffers the total loss over the path that she chose. And also we assume bandit feedback, which means that the learner only gets to observe this loss. So this can be generalized to a setting called combinatorial bandits or bandit combinatorial optimization, where the decision set of the learner is a subset of the discrete hypercube in D dimensions. So in the bandit shortest path example, D is the number of edges, and every element is a Boolean vector over the edges of the graph, where 1 indicates that an edge participates in the path and 0 otherwise. And we also assume that each element of S has exactly k non-zeros. So on round T, the environment picks some D-dimensional loss vector LT. The learner simultaneously picks XT from S, and she suffers the dot product between XT and LT. And also bandit feedback, so this means that she only gets to observe this dot product. So the goal of the learner is to minimize her expected regret, as usual, where the regret here is her total loss minus the total loss of the best fixed X in S. So this setting has been studied many times before. So Cesobianchi and Lugosi considered an algorithm which is exponential weights over the elements of S, where the exponential weight distribution is mixed with some uniform, with the uniform distribution for exploration. And this algorithm, for many important instances of this setting, yields an algorithm which is not only computationally efficient, but also gives optimal regret bounds. However, this idea doesn't work for bandit shortest path. So for example, you can take the grid graph, and if you look at it, if you sample a path uniformly at random, then the probability of choosing the edges on the outskirts of the grid can be very low if the grid is large. So they conjecture that, in fact, one can get k square root of dt regret. Capital T here is the number of rounds of the game. And they thought that this could be done by solving some semi-definite program to optimally choose the exploration distribution. So following that, Audibert, Boubec, and Lugosi, they realized that if we use, instead of uniform exploration, John's ellipsoid exploration, then we can get a guarantee of k to the 1.5 square root of dt. And this is for any combinatorial bandit instance, including shortest path. They also give a lower bound of k square root of dt. And they conjecture that this lower bound is tight. And they think that maybe mirror descent coupled with some regularizers that has a non-diagonal structure to the Hessian can give this regret bound. So our results are as following. First, for the bandit shortest path problem, we disproved the conjecture of Cesobianchi and Lugosi. And we showed that the algorithm from the previous slide has, in fact, tight regret. This implies, of course, a lower bound for the general case of bandit combinatorial optimization. And as well, we also get a lower bound for the bandit online ranking problem, which I'm not going to discuss in this talk. So how do we prove this result? So I'm going to focus on bandit shortest path. And first, I'm going to construct some worst case graph, in a sense. So this graph it consists of k over 2 layers, where for the learner to choose an ST path, in fact, what she has to do is to choose 1 over d over k vertices in each of the layers. Think about it like that. So what the environment does is it's first, before the game starts, chooses some x star, some path x star uniformly at random. This is going to be the optimal path. Then at every round t, the environment samples a univariate Gaussian random variable that has zero mean and sigma squared variance, and this is z. And then in each layer, on the edges on the left-hand side, if an edge is part of x star, then its loss is half minus epsilon plus z, and otherwise it's half plus z. And for the right-hand side, the losses are zero always. So sigma squared is chosen so these losses are bounded with high probability. So it's like 1 over log capital T. So what this construction yields is that the observed loss looks like a summation of k over 2 times this random variable z. And this means that its variance scales like k squared, which is crucial to the analysis. And also notice that because the learner only sees the sum, she cannot pick into the individual terms in the sum. This correlation doesn't help her in any way. In fact, comes for free to the environment. Okay, so this is not how we prove this, but just to give an intuition. So the goal of the learner is essentially to find this x star as quickly as possible. But she needs, what the intuition is that she needs roughly k squared sigma squared because of the variance of the loss, times d over k because she has to choose one of d over k vertices in each layer, over epsilon square rounds to identify x star. And until she does so, she suffers roughly k epsilon regret in each round. So if we choose epsilon in the worst case sense, we get the lower bound that we wanted. So to summarize, we disprove two conjectures. And in particular, we show that the optimal regret for bandit shortest path, it looks like k to the 1.5 square root of dt. And this is tight. But this only holds for worst case graph. So in the future, what we would like to do is to find the regret for specific graphs. And this is, this is not known even for the grid graph. We don't know what the regret is. Also, we couldn't prove a lower bound for the bandit online ranking case for the case of ranking n elements into n locations, which is also something we would like to do. And that's it. Thank you very much.
So we have time for one or two questions, if there's any.
Maybe just a comment. I mean, you didn't say that it's a weird result, right? Because in the full information setting, we know that the exponential weights are probably suboptimal.
That's right. Yeah.
Now you're showing that in the bandit case, suddenly exponential weights are optimal.
Yeah, but
So it's not a question, but can you just rephrase it?
Okay. So in the full information case, we know that exponential weights are suboptimal. There's a lower bound by Odibert, Nubek, and Lugosi. And this is, in fact, not the case for the bandit setting, which is somewhat surprising. But also notice that exponential weights is also suboptimal for multi-arm bandit because of the log factor. But here the log factor is crucial because the number of elements is exponential. And also, you assume usually that the loss is bounded in 0, 1, and here it can be between 0 and k. So k here comes squared. So yeah, so and that's the gist. That's the gist of it, basically.
Okay. Is there any other comment or question? No. Well, thanks again, Alon.